right, so before you went to lunch, you should have looked at, I know at least everybody finished dependent variable and most of you finished independent or at least got pretty far an independent variable. So what we're gonna do is we're gonna take this graph, and your original graph is always called the parent function. That's its name. So whatever graph you are working off of is called the parent function. So for example, if we're trying to change this parent function into the graph at the top left, there's 4 graphs, the one at the top left. What direction does the parent function move to get to that graph on the top left? Yeah, up. Specifically up by how many? 2. And we can also see that from the equation or expression, excuse me, by adding 2. What about the second graph? So the top right, how do we get from the parent 60, Selena? Or 80, excuse me, 80. How do we get from the parent to the second graph? How does it move? Parent to the second. If it helps, you can just look at the vertex. So if we look at where the vertex is here and where the vertex is in the second graph, that might be helpful. Nobody knows what direction it goes from the parent to this graph? Yeah, Amelia. Down 1. And we can tell that from the expression because it says -1, okay? Now, left to right is a little bit different. And I saw some of you ran into this when you're doing the independent variable. So if we just looked at the expression of x plus 2, and notice it's inside the parentheses, and here the plus 2 was outside the parentheses, what do you think plus 2 would do? Like thinking about it logically, yeah.
It would move right.
Move right. Unfortunately, it's not. It's the opposite. When you're inside the parentheses, you're going to do the opposite. I do have a way to prove this to you, but I will discuss it in March. I know that sounds like such a long time away, but for right now, just for our purposes, just trust me. A way you can remember this, and this is how I remember it too, if it's inside, it's the independent variable, and you do the inverse. So you do the opposite of what you would think. So for example, when we think plus, we all automatically on a number line think we're going to move to the right. But when we're talking about transformations, if it's inside the parentheses, we're going to do the opposite. So in this case, adding something would move our graph to the left, specifically left by 2 because it has a plus 2. What about if we were subtracting 1 inside the parentheses? What direction do you think that would go? Right, specifically right by 1. So remember, independent is in the parentheses. And that's going to move your graph left or right. And if you are dependent, you are outside the parentheses. And that's going to move your graph up or down. So independent is X, left and right axis, moving it left and right. Dependent is Y, up or down, which is the dependent variable, the Y, up, down, the Y axis. Hands up. Okay, so let's make some general rules. If we add something outside the parentheses, we're going to move up. And for this case, it is up by K units. K obviously would be some sort of number. In this case, we're just going to use K. So if we subtract something outside the parentheses, that would move it down K units. And again, this is where we need to think the opposite. So if we're adding K inside the parentheses, we're going to be moving left. And then if we're subtracting something inside the parentheses, we're going to be moving right. I can't spell. R-I-G-H-T. I'll give everybody a second. We're actually going to skip that first table. We're going to go to the let's practice, or the try at number 3 for the first one we do. So I don't like the table on the let's practice, I'll be honest. So we're going to skip it. All right, so for this first table, we have our parent, which is up here, and we're transforming it. We are transforming it by this. What operation is that? Multiply. We're multiplying by -1/2. Are we multiplying outside or multiplying inside? Outside. Nothing is happening inside those parentheses. So that means all of my x's are staying the same. -2, -1, 0, 1, and 2 stayed. -2, -1, 0, 1, and 2. Okay, but what we are going to do is all the output, the dependent variables, we're going to multiply them all by -1/2. So starting with 4. What is 4 times -1/2? -2. So that's going to be our new output. What is 2 times -1/2? -1. 0 times -1/2. 0. Again, 2 times -1/2 is still -1. And 4 times -1/2 is going to be -2. All right, I'm going to show you guys a picture like of this if it were graphed real quick. Oops. Undo. Maybe. There we go. Oh, okay, that's cool. It didn't save my graph. All right, so we have f of x equals, and that's x squared is the table that's there. So what about if we take -1/2? Oops. Oh my gosh, how do I go in? There we go. And multiply it by f of x. What happened to get my red graph to my blue graph? So what did the -1/2 do? Yeah, Madison. Okay, so I'm going to use reflecting. Is that okay? So that's a little bit more mathy. Okay, so reflecting. So I took the red graph, I reflected it down. Okay, so that's what the negative does. It takes it and flips it. What is the 1/2 doing to the graph? Yeah, Henry. We are multiplying it, but like visually, what looks different? It's not as obvious. I'll make it more obvious in a second. But between the red and the blue, they are a little bit different. Yeah, Asa. Yeah, the blue one's a little bit wider. So that 1/2 is making that graph a little bit wider. So what do you think would make it even more wider? That's not a word. Even wider. What could I do? What could I change about my equation to make it wider than it is now? Yeah. Okay, let's try that. What do you think would make it even wider? 1/8? 1/1000. Okay, so let's do 1/10. 1/100th. 1/1000th. Looks almost flat, but it's not. If I zoom out, it's not. 1 10,000th, 1 100,000th. Obviously, the smaller my fraction, the wider that graph is going to get. So thinking about the opposite, what's going to make that graph get stretched or skinnier? So this is a compression. And so when I say compression and I want to make this visual, I always use this hair tie. When I'm talking about compression, I'm talking about vertically. So if I push on this hair tie vertically, it stretches, right? Or it compresses this way. It makes it wider. So what would make it skinnier or stretch it? Yeah.
If you did it by like 2.
Okay, so anything greater than 1. So let's do it by 2. Okay, what would make it even more? Okay, let's try 20. What about 200 or 2,000 or 20,000? It's going to get skinnier and skinnier and skinnier. So almost looks like a line, but it's not. If we zoomed in, there is still space between those two sides. So when we multiply, if it is something less than 1, it's going to compress that graph, make it wider. If we multiply by something bigger than 1, it's going to stretch it or make it skinnier. So that's what happened here. Not only do we multiply by a negative, which flipped it, it also multiplied by half, which made it more compressed. Yeah, it would, Lauren. Good question. Okay, so let's look at a graph. So that was a table. Let's actually do it to a graph now. So here's our parent function, and we're doing 2 things to this graph. Adding 3 inside the parentheses and subtracting 2 outside. So what 2 directions does that tell us? So we're adding 3 in the parentheses, subtracting 2 outside. What would that be? Sarah, you know? Down to heck. Okay, use 2 directions.
Okay, down to the left.
Yeah, so left 3 plus 3 is left 3. Down 2 would be that subtracted by 2. So let me give you some advice on how to draw this. I would start with the vertex, which is the top of this. This is a parabola, by the way, in case you didn't know what shape this was. You want to move this vertex left 3 units and down 2 units. So 1, 2, 3, 1, 2. That's where our new vertex would be, at -1, -1. From there, just try your best to draw it. It doesn't have to be perfect. I'm not an artist, so don't judge me, but that's about as good as my drawing's going to be. I more care that your vertex is in the right place. That's what I'm going to be looking for. And that it generally looks like a parabola. All right, let's look at another graph. We're going to look at one more graph and one more table. So for this next graph, we're actually going to be making 2 transformations. So the first one, our new graph is x minus 3 in the parentheses. So what direction is that going to move? -3 in the parentheses. Right, yeah, right. So we're going to take, I'm going to take each of those 4 like corners and move them and then connect the lines at the end. So 1, 2, 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. And I would label that g of x because that's what it's saying that it's equal to, g of x. Okay, so we're going back to our parent, which was the black zigzag. We are now subtracting 3 outside the parentheses. So how's that going to move? Down 3. So we want to take each of those and move them down. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And that one is h of x. Give you just a moment and then we'll look at that last table. All right, that's last table. Here's my parent. And if I look at what I'm doing, I'm multiplying by a half and subtracting 3. Is anything happening inside the parentheses? No. So that means all of my x values are going to stay the same. So -4, -1, 0, 2, and 3 are going to be -4, -1, 0, 2, and 3. But all of my outputs, all of my dependent variables, all of my y's, we're going to multiply by a half and subtract 3. So 12 times a half is 6. 6 minus 3, my new output would be 3. For 6, half of 6 is 3. 3 minus 3 would give me an output of 0. For 4, half of 4 is 2. Minus 3 would give me an output of -1. 8, half of 8 is 4. 4 minus 3 would give me an output of 1. And then 10, half of 10 is 5. And 5 minus 3 would leave me with an output of 2. Output of 2.